And that was huge. That was a really big deal, and this is the first direct detection of gravitational waves and the first direct observation of black holes, which is kind of cool. And these are the results from the paper that we published with me and 1,000 of my closest colleagues. So let's take a step back. Let's say we want to build this new type of astronomy, which is really the goal for me. So we know that if we want to see things in the dark, nature's known for a long time that you need really big eyes to see in the dark. And astronomers have known this as well. And so we're building ever larger and larger telescopes. So the Keck telescopes on the left there are a pair of eyes that we have on Mauna Kea in Hawaii. These are sort of 10-meter scale telescopes. We put telescopes up into space all the time. We're trying to make them bigger and bigger. So the James Webb Space Telescope, the JWST there, is something like a $10 billion project to put a giant telescope up into space. And then here, the Giant Magellan Telescope we're working on at ANU, we actually have an $80 million investment in developing technology and building the Giant Magellan Telescope, which will go up on a mountaintop in Chile. And that's been, they've actually started building now. They've flattened the top of the mountain and they've started building buildings. And we're developing some of those techniques here at Mount Stromlo, just outside of Canberra, through the Research School of Astronomy and Astrophysics. So lots of big telescopes going on around the world. These are billion-dollar scale projects, even for the ground-based ones, and multi-billion-dollar projects for space. But if you want to see things that are really dark, that don't emit any light at all, nature also figured this out, that it helps to have really big ears as well. And so that's really what gravitational wave detection is like. We're building two giant ears for Earth, for humanity. And this is a picture of those detectors, so this shows where they are. And what they are giant Michelson interferometers. And to figure out why we're doing this, you need to figure out how gravitational waves interact with the world. So Einstein predicted that gravitational waves propagate at the speed of light as ripples in the curvature of space-time. And I still don't really know what the curvature of space-time means on an intuitive level. And so I like to think about the effect that it has on objects. So pretty much any time we want to measure gravity, we measure how it moves objects. So my whole expertise in laser metrology is about measuring the change in position of objects or the displacement of objects. So the way a gravitational wave works, if a gravitational wave was to propagate from me through you guys, it would cause you to become shorter and fatter 1 second, and then thinner and taller the next second. And so you oscillate in this quadrupole motion, like this. And if I had a ring of particles out in space, you imagine this ring would get distorted into an ellipse every time the wave oscillated through you. Now these waves are going through us all the time, but they're very, very small. So we've been looking for gravitational waves. Well, the LIGO project has been around for about 35 years. I've been working on it since 1996. The search for gravitational waves experimentally started actually in the 1950s. So it's been a really, really long time. And the reason it's taken us so long to detect these things is because they are so small. So if a very strong gravitational wave passed between the Earth and the Sun, the Earth would get closer to the Sun by about the diameter of a hydrogen atom. So it's a really, really small effect. It's something like 1 part in 10 to the 23 is what we need to measure. And so we can be forgiven for taking the better part of 60 years to measure these things. So LIGO are these giant interferometers. They're these laser interferometers that are designed to firstly make these pristine masses that we can measure the position of and shield them from all these external disturbances. And then secondly, measure those positions very accurately, or the change in the positions, using laser interferometry. So here's sort of a cartoon of how LIGO works. So we have a laser. We put it into a beam splitter that sends the light one way or the other. And then we put it onto these mirrors, which are 4 kilometers away. The reason they're so far away is because the gravitational waves produce a fractional length change, or a strain in space. So that means that longer arms means a larger effect that we can measure. And so what we do is we send the laser beams down each arm, we send them back, and when they combine, they interfere. And the interference means that they can interfere destructively or constructively. So the light will either go back towards the laser or towards a detector that we have. And now what happens is when these mirrors move very, very slightly, it changes the interference condition. So the laser wavelength is 1 micron, so 10 to the minus 6 meters. And so if you move the mirrors by a fraction of a micron, it can change the interference quite drastically. We're looking for displacements that are much, much less than a micron. We're looking for displacements that are 10 to the minus 18 meters. So this is a really, really challenging thing. If you think about the atoms that make up that mirror, are themselves around 10 to the minus 10, 10 to the minus 9 meters, we're looking for sort of a billionth of an atomic diameter change in the mirrors that are themselves made of atoms. So just to give you an idea of the scale, so this is an atom here, so there's like 10,000 atoms across a human hair, and then we zoom in, each one of these squares is a factor of 10, and that's the proton there. We keep on zooming in. The gravitational wave moved the mirrors by this much. So that's what we had to measure. And these mirrors themselves are made of atoms, which are all at room temperature. We don't cool anything down. There's no cryogenics involved. So these atoms are all jiggling around like this. But it's only because we have a very large laser beam that we get to average over billions and billions of atoms that we can get to this sub-proton measurement. So if we talk about measurements for a second, you've all probably heard of the concept of signal-to-noise ratio. And that's really what we are working with here, except we have the caveat that we can't affect the signal. The signal comes from black holes out in distant space, so we have no control over that. So all we can do is try and make our noise of our measurement system as low as possible. So if we think about what sort of noise could affect us at the 10 to the minus 18 meter level, pretty much anything you can think of will have an effect. And over many, many, many years of engineering effort by thousands of people, we've sort of isolated it down to a few key noise sources that we have to worry about. So the first one is residual gas. If we're shooting laser beams through air onto these mirrors, the density fluctuations in that air caused by turbulence or by temperature changes or even by thermal noise of the motions of the atoms themselves is enough that it will change the refractive index by many orders of magnitude more than we can tolerate if we are operating in an atmosphere. So the first thing we do is we get rid of the air. So that's one of the reasons LIGO is so expensive. LIGO needs these 4-kilometer long vacuum tubes which pump down to 10 to the minus 9 of an atmosphere. And they have to be very, very clean, very, very carefully controlled, very low vibration. But that gets rid of all of the gas. So we can get rid of the residual gas. The second thing is that we have to get rid of any other noise source that will shake the mirrors more than a gravitational wave. We want these mirrors to be pristine, just hanging there in space without being affected by anything else. And so the obvious one is seismic vibrations. So there's earthquakes going off around the world all the time. Like right now, there's little earthquakes happening. There's rumbling of the earth, and there's a background noise to the earth that we have to get rid of. And the way that we get rid of that is we use a very simple concept, which is the concept of a pendulum. So a pendulum, imagine I have a piece of wire and I have a mass on the end. If I move that top piece of wire very, very slowly, what happens is the mass at the bottom of that wire just follows my motion exactly. So that means the transfer function from the top to the bottom is basically unity. If I move the wire a little bit faster and I start to get to the resonance frequency, then what happens is the bottom moves a lot. So a little bit of motion at the top gives me a huge amount of motion at the bottom. And that's the resonance frequency, and that's bad. But if I can move it very, very, very fast compared to the resonance frequency of this pendulum, the bottom doesn't really move much at all. In fact, there's a huge attenuation, and the faster I move it, the larger that attenuation is. So that's the principle we use. So we put this mirror on the bottom of a pendulum, and we design the pendulum to be very, very big, so that the resonance frequency is very, very low, and that means above the resonance frequency, we attenuate a lot of the ground motion. Now, there's a lot of ground motion, and we have to attenuate a lot. So what we do is we take our large mirror at the bottom, we suspend it on the pendulum, and that pendulum is attached to a mass, which then we suspend from a pendulum, and then that's attached to a mass, which then we suspend from a pendulum, and then we do it a fourth time. And so we have a 4-stage pendulum system to give us f to the power of 8 suppression of this noise. So every stage of the pendulum gives you a 1 over f squared transfer function. We need 1 over f to the power of 8, and that's enough. If we then have active isolation on the top of the system, where we have normal seismic sensors and feedback systems to kill that. The next one is thermodynamic mirror surface fluctuations, and this is not changes in temperature. Even if we could control the temperature perfectly of the mirror, temperature is just the motion of the atoms that make up an object. And so these atoms are jiggling around quite a lot at room temperature, which is where we operate the interferometer, and so we have to figure out how to get rid of those. One of the things that we know, and this is sort of a physicsy thing that one of the only things about thermodynamics I still remember from undergraduate, is there's a half kT of energy in every mode of the system. And so we can either cool the mirror down, which we're planning on doing for future detectors, but it's actually quite difficult to do that and still operate the detector, or we can design the mirror in such a way that we put all of this energy into an area that we don't care about or that we don't look at. So the system that we use here is we build these mirrors that are really, really highly polished, very, very mechanically lossless.